I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'll be covering Gauss's law. As we'll see, Gauss's law is entirely equivalent to Coulomb's law. It's just a different way of looking at the same problems. Today we'll discuss not only how to derive Gauss's law, but also apply it to certain systems. And as we'll see, we'll have to apply it to systems that have a high degree of symmetry. Last time around, we defined what the electric field was, and the electric field due to a point charge is equal to the charge divided by 4 pi epsilon naught r squared in the radial direction. So this is an inverse square law. We also stated that the electric field obeys the superposition principle. So in other words, if you have a collection of charges, you can sum up the contribution from each of those charges separately. If you had a collection of in charges, the electric field due to those in charges at some field point or some observation point would just be a summation of each of these terms separately. Remember, R is the field point or the observation point if you prefer, and R represents the position of the ith charge. If you have a continuum of charges, it's convenient to express this in terms of an integral. And this is equal to 1 over 4 pi epsilon naught volume integral of the volume charge density rho, which is written as a function of prime coordinates, and times the separation vector r minus r prime over the magnitude of the separation vector cubed. So I want to emphasize that we are integrating over the prime coordinates, and that's because that's where the source is. Another concept that we talked about last time around was field lines, and there were 3 rules for field lines. Number 1, they originate on positive charges, they terminate on negative charges. Field lines don't cross, and furthermore, field lines extend or could extend into space as well. So we had a positive charge Q. The field lines would look like this, and of course you want to visualize it. It's more like a pin cushion, really, because we're just rendering this as in a 2-dimensional board, but you want to think of it as being a pin cushion and the ray lines extending radially outwards. So I'm going to use this concept to discuss flux. I should say flux can be understood in the concept of field lines. Flux basically tells you how much electric field you have passing through a certain area. So in the event, let's say that you're in a uniform or a region of space where the electric field is uniform, and we have some area A, and assume that this area A is coming in and out of the board. So in other words, the electric field lines are perpendicular to the plane of this window, if you will. So therefore, the electric flux is just E naught A. And as it turns out, if you have your electric field lines oriented differently, or your flux surface is taken in a different position with respect to your electric field lines, we have to generalize this expression. flux in that case would be equal to the electric field dotted into the normal to the surface. So in other words, if these electric field lines were coming in at an angle of 45 degrees with respect to this plane, then our flux would be E naught A cosine of 45 degrees. In the event that your field lines were along the plane, your flux would then go to 0. So let's take a look at having a box and determine what is the electric field, or flux rather, that passes through that box. And we'll assume this box is oriented such that its bottom back corner lies along the intersection of the x, y, and z axes. So the tops and bottoms are therefore parallel to our electric field, so there's no contribution from either of those. So we have top and bottom both vanish. From the front and back, likewise, we don't have any flux passing through those surfaces either. So flux for front and backs vanishes. The only places you'll have a contribution passing into and out of this square are on the left and the right hand sides. But remember, your normal is pointing out from the surface. So on the left hand side, your normal is pointing to the left. On the right hand side, the normal is passing to the right. And if I sum up the contribution from each of these terms, I see that my total flux is going to be 0. The flux lines enter, and then they exit. Let's suppose now that we don't have a uniform electric field. Let's suppose that we have a point charge. And my point charge is somewhere inside the box. And I want to figure out what's the flux out of the box. We know that the field lines extend outwards from the charge, and they're all going to be pointing outwards, and the normal's pointing outwards on each of the surfaces. So you would expect there to be a non-zero flux here. The question is how to calculate it. I'm going to look at a little bit simpler problem first, and I'm going to, or I should say what appears to be a simpler problem. I'm going to look at the flux through a sphere. And I'll place my charge at the center of the sphere. Bear in mind, this is not a real physical object here, the sphere. It's just a surface, mathematical concept, if you will. And I want to figure out what's the flux out of here. Well, I need to generalize my expression. Going through an area where my field's uniform, I'm going to turn this into an integral now. So now we're going to integrate this over the entire surface. And I'll put a circle on that integral sign to indicate that our surface here is closed. And I want to calculate this value here. Well, I know the electric field due to a point charge is just Q over 4 pi epsilon naught r squared. and in the r direction. Now the normal to the surface of a sphere is also in the radial direction. We're integrating over the surface area, and we're distance r away. So that surface element is going to be r squared sine theta d theta d phi. When I integrate over the surface of sphere, that's just going to give me a factor of 4 pi. See here too that the r carets dot each other out, and the r squared in the numerator cancels with the r squared in the denominator. And I'll wind up with q over epsilon naught. So this is my flux through this closed surface. This is Gauss's law. As it turns out, this holds not just for spherical surfaces, but for any surface. And it holds for any size surface as well. So let's consider two spheres that are concentric with each other. The first sphere has radius r. Call it capital R to distinguish it from this example on the other side of the board here. And I've got another surface that has radius 2r. So at first glance, it might appear, well, we're integrating over a larger surface area, so the flux would have to be larger going through this outer one than the smaller one. But that would ignore the inverse square law nature of the electric field. So on the left-hand side, if I calculate the flux through the smaller sphere, I'll wind up with q for 4 pi epsilon naught r squared in the r direction dot r squared sine theta d theta d phi. Once again, I'll wind up with q over epsilon naught. If I evaluate or calculate my flux through the larger sphere, that'll leave me with q over 4 pi epsilon naught 2r squared. Once again, we have r caret dot r caret, and this time we have 2r squared, quantity squared, rather than r squared sine theta d phi. So once again, these radial components of this interval cancel out. So even though the surface area is going to be 4 times larger if you're twice the distance away from the origin, your electric field also decreases by a factor of 4. So your surface area increases by 4, your electric field decreases by a factor of 4, and those two effects cancel each other out, and I see that once again the flux is just going to be q over epsilon naught. To generalize this even further, I don't need to have a sphere, because what holds over the whole area also has to hold for parts of the area. So if I break down my irregularly shaped surface into small components, once again I'll see that my electric field, rather the surface area or surface interval of my electric field is just going to give rise to a q over epsilon naught. Stated in plain English, flux through the electric field through any closed surface is proportional to the charge contained in that surface. So again, it doesn't matter how the surface is constructed, doesn't matter how regularly shaped it is. If there's charge inside of that surface, the flux will be proportional to it, and in fact it will be Q over epsilon naught. If I stick another charge inside of here, then my electric flux will now look like a summation. So if I don't just have one charge, but a whole collection of charges, if I have n charges, for instance, I just sum up all those QIs divided by epsilon naught, and that gives me the flux. If I have a continuum of charge, I can write this as a volume integral. So the surface integral of my electric field, dotted to the normal, is equal to 1 over epsilon naught times the volume integral of the volume charge density. So coming up, let's look at a few applications.